This is the last video with types of application problems. We're going to be talking about triangle congruence theorems. In the first video, I talked about Pythagorean theorem applications. In the second video, I talked about 30, 60, 90 triangle theorem, and also briefly about how you could use the Pythagorean theorem to solve that same problem. In type 3, we talked about 45, 45, 90 triangle theorem, and then I also briefly modeled how to use the Pythagorean theorem to solve that same problem. Remember that for type 2 and 3, the way that we solved those theorems in the first place was using the Pythagorean theorem. So either of these types of problems can be solved using the Pythagorean theorem, but they do require thinking back to how we did the proof in the first place. So there are other triangle congruence theorems that you could be asked to do, and so in type 4, that's what we are going to talk about. So satellite A is 2,000 kilometers above the surface of the Earth, and we want to know how far satellite A is from another satellite, satellite B. We also want to know how far above the Earth's surface satellite B is, and we are assuming the radius of the Earth is 3,960 miles. Oops, that is not the correct problem. Just a second. I'm going to skip that problem and go down here. If you did that problem, great, but I'm skipping to this one. We have 4 satellites are orbiting the Earth as shown in the diagram, so that segments BD and AC intersect at the center of the Earth. So let's look at the picture because that doesn't make any sense without the picture. 4 satellites shown orbiting the Earth, so that segments BD and AC intersect. So this is supposed to be an intersection of 2 lines. You want to think to yourself, oh, what does that mean? Oh, that means this line segment, this angle and this angle are going to be congruent. Those are vertical angles right there. All right, satellite A and C are both 1,800 kilometers above Earth's surface. So this A and this C, this length here is 1,800 kilometers. And this length here is 1,800 kilometers. Notice I'm just labeling the problem with what I know. And if satellite D is this far above the surface of the Earth, satellite D is this far. How far is satellite B? So we're trying to figure out how far this is from the surface of the Earth. All right, I'm noticing I have a triangle here. I have a triangle here. They look similar to each other. Is there a way that we can prove that they are identical? Because if we can prove that this is congruent to this triangle, then we would know instantly that this answer and this answer are the same. Well, what I mentioned before about vertical angles, this angle, if I put an E here, I don't know if you can see my E, but there is an E here that I drew in. Then I could say that this angle and this angle are congruent to each other because they're vertical angles, or the vertical angle theorem. And these 2 pieces, they were told to us more or less were congruent because this is the radius of the Earth and this length, and this is the radius of the Earth and this length. So, I mean, that's kind of given to us. And then angle A and angle C, this angle and this angle here, these 2 angles are right angles, and all right angles are congruent to each other because of the right angle congruence theorem that we've talked about before. And so I have an angle, a side, and an angle that are matching each other. Angle, side, angle, angle, side, angle. And so the 2 triangles are congruent by the angle, side, angle congruence theorem. And because the 2 triangles are congruent, then we can say that this length and this length are also the same because congruent parts of congruent triangles are congruent. And since we know that these parts and these parts are going to be the same, and that this is a circle with the radius exactly equal on both sides, we could say that since satellite D is 3,572 kilometers above the Earth, and that means satellite B is also 3,572 kilometers above the Earth. Most of this problem has very little to do with the actual numerical calculations that are here. There are other ways that you could have solved this problem. You could have tried to use the Pythagorean theorem. So here we could, this length and this length, we know them. We could add those together. This length and this length, we know them. We can add them together. Then we'd have the hypotenuse on one side, so we could find the third side, and we could show that this right triangle, we know all the lengths of this right triangle. And then you could try and establish that if something else. But eventually, you would have to prove that this triangle and this triangle are the same. Because really all we can find is this piece of information over here. So we could find all three parts of this triangle. But unless you can somehow establish that this triangle is the same, we wouldn't be able to solve this problem. We do have the hypotenuse and an angle that match. And we have a hypotenuse. Sorry, not a hypotenuse. We don't know the hypotenuse. That's what we're trying to find here. We have a right angle and another angle. For this particular question, I am only seeing angle side angle, but there might be another way to solve it. I hope that question was helpful.